Okay, it is now time to move on. We will actually be doing sections 5.2 and 5.3 kind of at the same time. I want to mix what's done in those two. So like I said, section 5.2 and 5.3. And what those do is they talk about definite integrals and the fundamental theorems of calculus. First thing I want to do is I want to recall a concept from section 4.10. And what this said was let f of x be a function capital F of x is the antiderivative and the integral of f of x dx is called the indefinite integral. Again, this is what we did in section 4.10, and pretty much what we said that this was it was the derivative, but backwards, right? So now I'm going to define a new type of integral. If f of x is a function defined on an interval a to b inclusive, then the definite integral of f from a to b is integral from a to b of f of x dx equals the limit as n goes to infinity of f of xi star times delta x. Now, this notation is not one we are going to use a whole lot in this class. In fact, we're not really going to use it at all. But I'm going to first really quickly explain kind of what this is, okay? Remember in section 5.1, our last class, we talked about if I have a curve and I want to know how much space is from here to here, I'm going to break this up into smaller parts, right? So I would do like this, and then just keep doing it into smaller pieces, right? What this is trying to say is what happens as each piece gets smaller and smaller, right? So instead of having that many parts, I'm going to break it into even smaller parts. And then even smaller parts. And then even smaller parts. And even smaller parts. And as you can see, as I break it into more and more pieces, it ends up taking up the entire space. That's what that means here. Okay? It just means if I break this into significantly smaller pieces, then what happens? Okay? Like I said, we are not going to use this a whole lot, but I do want to talk a little bit about it. First things first, as we can see right here from what happens there, the area under a curve is given by the integral from a to b of f of x dx. This is a big point we are going to use a lot throughout Calculus 1, 2, and on. Okay? This is going to be a really big point here. What I want to learn here in 5.2 and 5.3 is how to find this without having to actually break this into a bunch of smaller pieces. Okay? But before we do that, I want to talk a little bit about the properties of a definite integral. So properties of definite integrals. The first one is that if I have the integral from a to a of f of x. So if my bounds are the same thing, so like 1 to 1, 2 to 2, that kind of thing, that's going to be equal to 0. And the reason is because if my endpoints are the same, then I don't have any space here, right? Because if it's just one part, that's just one line, and so I don't have a bunch of space right here. Okay, that's why that kind of makes sense. So if my bounds are the same, I get 0. If I'm going from a to b of f of x dx, and if I wanted to flip them, I would change my sign. So negative integral from b to a of f of x dx. Another thing is if I am adding or subtracting, so like f of x plus or minus g of x dx, I can split this into two different terms and go from a to b of f of x, and then from a to b of g of x. Again, I can just split them up. Another rule, this is a rule we have seen a bunch and are going to see a bunch more times. If I have a constant, I can just bring that constant out to the front. I can just bring it out front. And then another rule is really cool, and this is that I can split it up into two different parts. So like if I'm going from a to b of f of x dx, I can pick a point between them, say c. I can pick a point between them and go from a to c, and then add it going from c to b. So I can break it up into two parts if I need to. Let's see an example on how these rules might help us out. So example. If it is known that the integral from 0 to 8 of f of x dx is equal to 10, and that the integral from 0 to 5 of f of x dx is equal to 5, then find the value of the integral from 5 to 8 of f of x dx. So I know from 0 to 8, and I know from 0 to 5, so I want to know what it is from 5 to 8. Okay. Well, I know the integral from 0 to 8 of f of x. From our rules, I know I can split this up if I have to. So since I know what happens from 0 to 5, why don't I split it up starting from 0 to 5? So then I would have to add, if I originally went from 0 to 8, and I've already gone from 0 to 5, what I have left is to go from 5 to 8, which is actually good because that's what they wanted, right? That's what they did want. So that's really nice. I know from 0 to 8, I get 10, so this should be 10 equals. I also know from 0 to 5, I get a 5 plus the integral that I want, integral from 5 to 8 of f of x dx. So then all I've got to do then is subtract 5, and I see that 5 is equal to the integral from 5 to 8 of f of x dx. So this is just a helpful way I can use the rules we just said. All right, so now I want to work towards actually finding what an integral is. That's what I want to do. The first way I'm going to do that is with the fundamental theorem of calculus. But this is only part 1. We will get to part 2 here soon. This is part 1. This says if f of x is continuous over an interval from a to b, and the function capital F of x is defined by capital F of x equals the integral from a constant to x, so a to x, of f of t dt, then the derivative of capital F of x is equal to lowercase f of x. So notice the notation here, okay? It's a constant to x. Keep that in mind. It's got to be a constant to x. It doesn't matter what this constant is, but this is an x. Keep that in mind. So let's look at an example of that. Let's let g of x be equal to the integral from 1 to x of 1 over t cubed plus 1 dt. And I want us to find the derivative of that. So from this rule we just did, notice this has the exact form here, right? A constant is the lower bound, and x is the upper bound of something in terms of t. So this has the exact form as what I had here. Okay. So all I've got to do then, based on what I said up here, the derivative of that is just f at that point x, right? F of x. So all I've got to do is plug in the x here. And we get 1 over x cubed plus 1. That's it. That's all I've got to do based on this rule here. But to be clear, it's got to be a constant down here and an x here. If that happens, I just have to plug in x to find what the derivative is. Let's look at another example. Let's let capital F of x be equal to the integral from 1 to the square root of x of sine t dt. And I was to find the derivative of that. All right. This one does not have that specific form, okay? Because down here is good because I have a constant. But look up here, I have square root of x, not just x, okay? So since this is a function of x and not just an x, I've got to use the chain rule we learned in chapter 3, okay? So remember what the chain rule said was to keep this the same. So I would do sine of the square root of x. But because of the chain rule, I have to multiply that by the derivative of the square root of x, which is 1 over 2 square roots of x. So again, this first part we get from the fundamental theorem of calculus part 1. And then this part is from the chain rule because then I have to multiply that by the derivative of the square root of x. On that note, let's look at another example. Let's let capital F of x be equal to integral from x to 2x of t cubed dt. Now this one's wrong for a lot of reasons. Because first of all, my lower bound is not a constant. And up here I have 2x, not just x. So then I've got to make this into the form that I want. I want to have one of the bounds being a constant. So using our rules that we learned, let me find that board where we talked about them. Right here, I can use this last rule and split it into 2 using a constant. Okay, it does not matter what the constant is, so I'm going to just use 0. Okay, so if I wanted to split this up, oh, and sorry, the whole point is we're finding the derivative of that. So if I wanted to split this up, I'm just rewriting it right now. I could split it up from x to 0. Again, it does not matter what my constant is. It just has to be a constant. And then add that, go from 0 to x squared. Just like that. This one's good because I have a constant here, and then, oh, that should be 2x, not x squared. Apologies. I have a constant here and then some stuff up here, right? But this one, my constant is on top. So I want to flip those. Remember we said in our rules, to flip them, I have to change my sign, right? So I want to flip these, so make it negative integral from 0 to x of t cubed dt, plus, this one's fine, 0 to 2x t cubed dt. Now I can take the derivative using that. That's capital F of x, so I can take the derivative. For the first one, I have a constant here and just an x there, so then that's fine. So I can just plug in x, so this gives me negative x cubed. But for this one, I would plug it in and then multiply it by the derivative of 2x because of the chain rule. So it would be plus 2x cubed times the derivative of 2x, which is just 2. So if you wanted to, you could write this out as a simplified version. Negative x cubed. 2 cubed is 8. 8 times 2 is 16. So plus 16x cubed. Combine like terms, and you get 15x cubed. Just like that. So the key thing here, I need a constant and an x. If I don't have an x here, I have to use the chain rule like I did here and right up here. From this first fundamental theorem of calculus, we can move on to part 2. And part 2 is a really big deal. We are going to use this a lot in Calculus 1, Calculus 2, Calculus 3, and everywhere else. Okay, this is a really big deal, so put a star by it, highlight it, whatever you've got to do. This is the fundamental theorem of calculus part 2. And what this says is that if f is continuous over the interval a to b, and if capital F of x is the antiderivative of f of x, then the integral from a to b of f of x dx is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. This is a really big deal, so like I said, put a star by it, highlight it, whatever you've got to do. Okay. So what I would do is take the antiderivative. After that, plug in b, plug in a, subtract them. So let's look at an example. Integral from 3 to 9 of 2x dx. integral from 3 to 9 of 2x dx. So remember, like I said up here, all I do is find the antiderivative of 2x. So I'm going to do that first. Remember, I've got to think about what function has a derivative of 2x. Well, I know that's x squared, right? The derivative of x squared is 2x, so the antiderivative of 2x is x squared. And I'm going to do x squared from 3 to 9. Okay, and like we said up here, what that means is plug in my top bound and then plug in my bottom bound and subtract them. So start with my top bound, that's a 9, so 9 squared. Then subtract, plug in this bound, so 3 squared. 9 squared is 81, minus 3 squared, which is 9. Subtract those and you get 72. 72. So again, find the antiderivative, plug in 9, plug in 3, subtract them. Another example, integral from negative 2 to 2 of t squared minus 4 dt. All right, so the same thing. I'm going to find the antiderivative of this, and then plug in 2, plug in negative 2, and then subtract them. Okay. So first things first is I need to find the antiderivative of this. Remember, we had a reverse power rule, which means I normally bring my power down and then minus 1, right? That's how I take the derivative. But if I want to go backwards, I have to add 1, making it t to the third, and then divide it by my new power. So divide it by 3. Do the same thing here. Since I just have a 4, it becomes 4t. Again, because the derivative of 4t is equal to 4. So remember, I want to go backwards. And I'm doing that from negative 2 to positive 2. So I'm going to start by plugging in a 2. So that's going to be 2 cubed over 3 minus 4 times 2. And then subtract, plug in the negative 2. So minus negative 2 cubed over 3. But I'm subtracting, which will make this a plus 4 times the negative 2. Let's work this out. 2 to the third is 8, so that's 8 thirds. Negative 4 times 2 is negative 8. Negative 2 cubed is negative 8, but I am subtracting that, so that's going to make it positive 8 thirds. 4 times the negative 2 is negative 8. 8 thirds plus 8 thirds is equal to 16 thirds. Negative 8 minus 8 is minus 16. You need a common denominator, which would be a 3. So 16 over 3 minus 16 times 3 is 48. 16 minus 48 is negative 32. So negative 32 over 3. Again, all I do is take the antiderivative and then plug in your top bound, plug in your bottom bound, and then subtract them. Another example, we're going to do quite a few more. Integral from negative 3 to 0 of 4x to the 1/3 dx. All right, so again, how I start is I'm going to find the antiderivative. So remember how I do that is I'm going to add 1 to my power. Remember, 4 just stays 4. 1/3 plus 1 is 4 thirds. So x to the 4 thirds. and then divide by my new one. So divide by 4/3. Well, 4 divided by 4/3 is like doing 4 times, flip it, and do 3/4. The 4's cancel out, and we're left with just 3. Forgot to write this, but that's okay. So if I divide 4 by 4/3, that's just 3. So we get 3x to the 4/3 to the power of, from -3 to 0. Plug in my top bound first, plug in a 0, minus, plug in a -3. 0 to the 4/3 is equal to 0, so then this whole term is just gone, which leaves me with -3 times -3 to the -4/3, or that should be positive 4/3, I don't know where I got that from, positive 4/3, and since there's really no other way to simplify that, you can just leave that, and that's fine. -3 times -3 to the 4/3. So once again, just take the antiderivative, which we did in section 4.10, plug in my top bound, plug in my bottom bound, and then subtract them. Another example, integral from 4 to 6 of 1 over x dx. So once again, I need to take the antiderivative of 1 over x. Okay, so then I've got to think about it. What function has a derivative of 1 over x? Well, that would be the natural log of x. So the natural log, absolute value of x, is the antiderivative. But I'm doing that from 4 to 6. So plug in a 6. The absolute value of 6 is just still a 6. So natural log of 6 minus, plug in a 4. The absolute value of 4 is just a 4. So natural log of 4. Easy enough. Some more examples. Integral from 1 to 5 of x cubed minus 4x squared plus 3x minus 2 dx. Remember, the first things first is I'm going to take the antiderivative, add 1 to my power, and then divide by that thing. So add 1, we get a 4. So x to the 4th over 4. Same thing here, add 1, we get a 3 to divide by 3. So 4x to the 3rd over 3. Add 1 makes it a 2, divide by 2, so we get 3x squared over 2. And then 2 just becomes 2x. Again, because the derivative of 2x is just 2. Doing that from 1 to 5. So first, again, a 5. 5 to the 4th, that would be 5 times 5 times 5 times 5, which is 625 over 4. 5 to the 3rd is 125. 125 times 4 is 500. 500 over 3. Plug in a 5 right here. 5 squared is 25. Times 3 is 75. So 75 over 2. Plug in a 5. 5 times 2 is 10. Now subtract and plug in a 1. So subtract, plug in a 1. 1 to the 4th is 1. So 1/4. I'm subtracting it, which would make this plus. Plug in a 1. 1 to the 3rd is just 1. So that's 4/3. Subtracting, so change that sign, plug in a 1. 1 squared is 1, so that's just 3 over 2. And then plug in a 1 right here, you get negative 2, but since I am subtracting, that's going to be you get plus 2. So, combining all of this stuff, 625 over 4 minus 1 over 4 gives me 624 over 4. Negative 500 over 3 plus 4 over 3 gives you negative 496 over 3. 75 over 2 minus 3 over 2 gives you 72 over 2. Negative 10 plus 2 is negative 8. 624 over 4 gives you 156. 496 over 3, I think, can be divided. I'm trying to do it in my head. Maybe not, actually. Let me see. Let me try. Stop trying to be cool and just do it. 496 over 3, maybe not. Yeah, no. So that's going to stay. 72 over 2, though, is 36 minus 8. 156 plus 36 minus 8 is 184. So 184 minus 496 over 3. I need a common denominator, which would be 3. So 552 over 3 minus 496 over 3. Subtract those. And you get 56 over 3. So after all that, 56 over 3. Again, the key thing here is just to just take the antiderivative, plug in my top bound, plug in my bottom bound, subtract them. A few more examples. Integral from 1 to 9 of x minus 1 over the square root of x dx. Now this one at first glance looks pretty hard, but remember, since we have two terms on top and only one term here, I can actually split these into two terms. Okay, so I can make this integral from 1 to 9 of x over the square root of x dx minus integral from 1 to 9 of 1 over the square root of x. And then I can try to rewrite these so that they kind of help me out. So x over the square root of x is like doing x over x to the 1/2. So and then if I subtract those, that's x to the 1/2. So this first one is just integral from 1 to 9 of x to the 1/2 dx. And then 1 over the square root of x, that's like 1 over x to the 1/2. So since it is in the denominator, I can make it x to the negative 1/2. And so now I just need to find the antiderivative. I do that by adding 1. 1/2 plus 1 is 3/2. So this is x to the 3/2 over 3/2 minus, do the same thing over here, negative 1/2 plus 1 is 1/2. So x to the 1/2 over 1/2. And I'm going to first plug in a 9, then plug in a 1. So plugging in a 9 to the 3/2, that's like doing the square root and then raising it to the third. So the square root of 9 is equal to 3. 3 to the third is 27. Dividing by 3/2 is like multiplying by 2/3. And then minus, plug in a 9 here. 9 to the 1/2 is like doing the square root. So so the square root of 9 is equal to 3. Dividing by 1/2 is like multiplying by 2. Then subtract, plug in the 1. So minus 1 to the 3/2 is just a 1. And then dividing by 3/2 is like multiplying by 2/3. Minus, which would make it a plus. 1 to the 1/2 is just a 1. And then dividing by 1/2 is like saying times 2. Simplify this. 27 over 3 is 9. 9 times 2 is 18. 2 times 3 is 6. 2/3 is just 2/3. Plus 2. 18 minus 6 is 12. 12 plus 2 is 14. Get a common denominator, which would be 3. So this would be 42 over 3 minus 2 over 3, which is 40 over 3. So one more time, all I'm trying to do here is find the antiderivative and then plug in my bounds. Now where this is really helpful is based on something I wrote down at the very start of class. Let me see if I can pull that back up. And that is that the area under a curve is just the integral from a to b of f of x. So knowing this fact right here is going to help us out a lot. Example. Find the area under the curve f of x equals 4x minus 9 from x equals 2 to x is equal to 5. So what this means, based on what I said a while ago, what I'm really wanting to do is the integral from 2 to 5, so 2 to 5, of 4x minus 9 dx. This is what I want to do. So just like we have said, how I do this is I take the antiderivative of 4x minus 9, add 1 to the power would make it a 2, so x squared, divide by 2, 4 divided by 2 is 2. So 2x squared. And then for 9, it's just 9x. Again, because the derivative of 9x is just 9. And I'm doing that from 2 to 5. So first, plug in a 5. 5 squared is 25 times 2 is 50. Plug in a 5 right here. 9 times 5 is 45. And then subtract. Plug in a 2. 2 squared is 4. 4 times 2 is 8. Subtract, which would make this a plus. 9 times 2 is 18. 50 minus 45 is 5. 5 minus 8 is negative 3. Negative 3 plus 18 is 15. So my point here is now, instead of having to do all of those rectangles like we have done, I can do this instead, and it is a lot less work, and it will be exactly right. One more example, and then we will be done with this section. Find the area under the curve y equals sine of x from x equals 0 to x equals pi over 2. So just like I did up here, how I do this is a equals the integral. We're going from 0 to pi over 2 of sine of x. So I need to find the antiderivative of of x. Well, I know the derivative of cosine is equal to negative sine. So since this is positive sine, we know it's going to be negative cosine. Again, because the derivative of cosine is equal to negative sine. So since this is positive, it's got to be negative. From 0 to pi over 2. Plug in pi over 2, negative cosine of pi over 2. Subtract, which would make it a plus. Plug in the 0. So now I just have to know what cosine of pi over 2 and what cosine of 0 are. So if we break out our unit circle, of which I am trying to find on my desk right now, I normally have it just laying out, and for some reason it is not. But if you look at the unit circle, what we will find, cosine of pi over 2 is right here. Cosine is equal to 0, so that's going to be 0, plus cosine of 0, which is right here, is equal to 1. 0 plus 1 is 1. All right, that is the end of sections 5.2 and 5.3. We are going to use these skills throughout the rest of this class and a lot throughout Calculus 2. So if any of it does not make sense, please let me know.